City Electrical Inspector's interpretation concerning the active harmonic filter installation is not correct. National Electrical Code, Section 240.21c3 dictates the overcurrent protection needed for conductors that tap off a feeder, and the protection must be based on the ampacity of the feeder itself and not based on the load that is supplied by the tap. The 4000 amp bus in this specific scenario acts as the feeder. Therefore, the 125 amp breaker tapping off the bus has to be correctly sized to protect the conductors that connect the tap to the active harmonic filter. Considering that the ampacity of number 2 conductors is approximately 95 amps, the 125 amp breaker is oversized. This potentially creates a safety hazard because the oversized breaker wouldn't provide sufficient protection to the conductors should there be a fault. If the fault current surpasses the ampacity of the conductors, these conductors could overheat, which may result in a fire. The appropriate method for installing the active harmonic filter involves connecting it to the 4000 amp bus while using conductors that are properly sized according to the filter's ampacity, which is specified at 100 amps. This ensures the conductors have overcurrent protection if a fault were to occur. It is essential to remember that the National Electrical Code stipulates that all electrical installations must adhere to safety standards and comply fully with the code. Installing the active harmonic filter while strictly following the National Electrical Code guidelines helps to ensure both the safety of the overall installation and the safety of personnel working on or in proximity to the equipment. Now let's delve a bit deeper into the specific aspects of the National Electrical Code that pertain to this situation. The National Electrical Code, Section 240.21, covers the rules surrounding overcurrent protection for feeder taps. A feeder tap is essentially when you take power from a larger feeder circuit to supply a smaller load. The rules are in place to ensure that the smaller conductors used in the tap are adequately protected. Section 240.21c specifically addresses tap rules for feeders. There are several conditions that must be met when tapping a feeder to ensure the safety of the installation. In the particular case described, Section 240.21c3 is most relevant. This section outlines the requirements for feeder taps not over 25 feet in length. The rule states that the ampacity of the tap conductors must not be less than 1/3 of the ampacity of the feeder conductors from which they are tapped. In addition, the tap conductors must terminate in a single circuit breaker or a single set of fuses that will limit the load to the ampacity of the tap conductors or less. The overcurrent device must be rated no more than the ampacity of the tap conductors. Applying this to the scenario at hand, the main feeder is a 4000 amp bus bar. The tap conductors are number 2 copper conductors which have an ampacity of approximately 95 amps, according to National Electrical Code Table 310.16, assuming they are rated for 75 degrees Celsius termination. 1/3 of the ampacity of the 4000 amp feeder is 1333.3 amps. Since the ampacity of the tap conductors, 95 amps, is less than 1/3 the ampacity of the feeder conductors, this condition is met. The tap conductors terminate in a 125 amp circuit breaker. However, this violates the rule that the overcurrent device must be rated no more than the ampacity of the tap conductors. The 125 amp breaker exceeds the 95 amp ampacity of the number 2 conductors. Therefore, the installation as described does not comply with the National Electrical Code, Section 240.21c3. To correct this, the 125 amp breaker should be replaced with a breaker that is rated 95 amps or less. Alternatively, larger conductors could be used for the taps so that their ampacity is greater than or equal to the rating of the 125 amp breaker. However, simply increasing the conductor size without changing the breaker would still violate the National Electrical Code, as the overcurrent protection must be sized appropriately for the conductor ampacity. It's crucial to understand the intent behind these code requirements. The overcurrent protection device, whether it's a circuit breaker or a fuse, is designed to protect the conductors from overheating due to excessive current flow. If the breaker is too large, it will allow more current to flow through the conductors than they are rated for. This can cause the conductors to overheat, potentially damaging the insulation and creating a fire hazard. In the described scenario, the active harmonic filter is intended to reduce harmonic distortion in the electrical system. While the filter itself may only draw 100 amps, the tap conductors must still be protected based on their ampacity. The fact that the filter is not drawing a full 125 amps continuously does not change the requirement for overcurrent protection. The overcurrent device must be sized to protect the conductors, not just the load. Furthermore, it is important to consider the potential for fault currents. A fault current is a very high current that can flow in the event of a short circuit or ground fault. These fault currents can quickly overheat conductors and cause significant damage. The overcurrent protection device must be able to interrupt these fault currents quickly to prevent damage and ensure safety. An oversized breaker may not trip quickly enough to protect the conductors from a fault current. Therefore, it is essential to select the correct overcurrent protection device based on the conductor ampacity and the available fault current. It's also worth noting that the National Electrical Code is updated regularly to reflect changes in technology and best practices. It's important to stay up to date on the latest code requirements to ensure that electrical installations are safe and compliant. Consulting with a qualified electrical engineer or inspector can also help to ensure that installations meet all applicable codes and standards. In summary, the proposed installation of the active harmonic filter with a 125 amp breaker tapping off a 4000 amp bus using number 2 conductors does not comply with the National Electrical Code, section 240.21c3. The 125 amp breaker is oversized for the ampacity of the number 2 conductors. To correct this, the breaker should be replaced with one that is rated 95 amps or less, or the conductors should be increased in size to match the breaker's amperage. It's crucial to prioritize safety and compliance with the National Electrical Code in all electrical installations. The National Electrical Code, section 110.3b, mandates that listed or labeled equipment must be installed and used in accordance with any instructions included in the listing or labeling. Active harmonic filters are commonly listed devices, meaning they've been tested and certified by a recognized testing laboratory like Underwriters Laboratories or Intertech. The installation instructions that accompany the harmonic filter typically specify the required overcurrent protection and conductor sizing. Failing to adhere to these instructions would violate National Electrical Code 110.3b and could potentially void the equipment's warranty or insurance coverage. Let's briefly discuss the role and impact of active harmonic filters. Harmonic distortion in electrical systems arises from nonlinear loads. These loads draw current in a non-sinusoidal manner, injecting harmonic currents back into the power system. Common sources of harmonics include variable frequency drives, electronic ballast, and other power electronic equipment. Harmonic currents can cause a variety of problems, including overheating of transformers and conductors, malfunction of sensitive electronic equipment, and increased energy losses. Active harmonic filters work by injecting currents into the system that are equal in magnitude but opposite in phase to the harmonic currents produced by the nonlinear loads. This effectively cancels out the harmonic currents, reducing the overall harmonic distortion in the system. By reducing harmonic distortion, active harmonic filters can improve power quality, reduce energy consumption, and extend the life of electrical equipment. In industrial facilities, active harmonic filters are often installed at the main switchboard or at individual loads that generate significant harmonic currents. The size and type of filter required depends on the amount of harmonic distortion present in the system and the sensitivity of the equipment being protected. Properly installed and maintained active harmonic filters are an effective solution for mitigating harmonic distortion and improving power quality in electrical systems. Moreover, the requirement to adhere to the National Electrical Code isn't merely about compliance, it directly contributes to the safety and operational efficiency of electrical systems. Non-compliance can result in a multitude of negative consequences, varying from equipment malfunction to increased risk of electrical fires and severe injuries. Electrical inspectors play a crucial role in upholding these safety standards, but the ultimate responsibility rests on the qualified personnel performing the electrical work to possess a comprehensive understanding of the National Electrical Code and to apply its principles diligently. When discrepancies arise, such as in the scenario described, open and collaborative communication between the electrical inspector, the plant engineer, and the electrical contractor is essential to ensure that all decisions are aligned with the National Electrical Code and prioritize safety above all else. Consider documenting all interpretations and decisions made during the installation process, especially when there are disagreements or deviations from standard practices. This documentation can serve as a valuable reference in the future and can help to clarify any questions or concerns that may arise. Always prioritize safety and compliance with the National Electrical Code in all electrical work. The plant engineer has a duty to ensure safety, as well as that the design will work. While it may be frustrating to hear an interpretation that is not correct, explain why you believe the interpretation is not correct and cite the specific code section you are referencing. The electrical inspector has a responsibility to ensure that the installation meets the minimum safety requirements of the National Electrical Code. If there are concerns about the interpretation of the code, it is important to discuss them with the electrical inspector and come to a mutually agreeable solution. If a mutually agreeable solution cannot be reached, it may be necessary to appeal the electrical inspector's decision to a higher authority. Remember that the goal of the National Electrical Code is to protect people and property from the hazards of electricity. By following the code, electrical workers can help to ensure that electrical installations are safe and reliable. Another important aspect to consider is the voltage drop across the conductors. The National Electrical Code, Section 210.19a on Informational Note No. 4 and Section 215.2a3 Informational Note No. 2 recommends that the voltage drop on feeder and branch circuit conductors should not exceed 3% for power, heating, and lighting loads, or 5% for feeders and branch circuits combined. Excessive voltage drop can cause equipment to operate inefficiently or malfunction. In the described scenario, the conductors are relatively short, less than 25 feet, so voltage drop may not be a significant concern. However, it's always good practice to calculate the voltage drop to ensure that it is within acceptable limits. The voltage drop can be calculated using a formula that takes into account the conductor length, current, and resistance. There are also many online voltage drop calculators that can be used. If the voltage drop is too high, the conductor size can be increased to reduce the resistance and lower the voltage drop. Also be mindful of conductor directing factors. The ampacity of a conductor is the maximum current that it can carry continuously under specific conditions. However, the ampacity of a conductor must be derated under certain conditions, such as when it is installed in a high-temperature environment or when multiple conductors are bundled together. National Electrical Code Table 310.15 bone contains correction factors for ambient temperature, and National Electrical Code Table 310.15 cone contains adjustment factors for the number of current-carrying conductors in a raceway or cable. These derating factors must be applied to ensure that the conductors are not overloaded. In the described scenario, it is important to consider the ambient temperature and the number of conductors in the raceway or cable. If the conductors are installed in a hot environment or if there are multiple conductors bundled together, the ampacity of the conductors must be derated accordingly. It's also important to ensure that all electrical connections are properly made and tightened. Loose connections can cause overheating and arcing, which can lead to fires. All connections should be made using approved connectors and should be tightened to the manufacturer's specifications. Periodically inspect electrical connections to ensure that they are still tight and in good condition. Another crucial aspect to consider is grounding and bonding. Grounding is the process of connecting electrical equipment to the earth to provide a path for fault current to flow back to the source. Bonding is the process of connecting non-current carrying metal parts of electrical equipment together to create a low impedance path for fault current. Proper grounding and bonding are essential for safety. They help to prevent electric shock and reduce the risk of fire. The National Electrical Code contains detailed requirements for grounding and bonding. It's important to follow these requirements carefully to ensure that the electrical system is properly grounded and bonded. Remember, electrical work can be dangerous. Always take precautions to protect yourself from electric shock. Wear appropriate personal protective equipment such as insulated gloves and safety glasses. De-energize circuits before working on them and use lockout/tagout procedures to prevent accidental re-energization. If you are not qualified to perform electrical work, hire a licensed electrician. It is not worth risking your safety or the safety of others by attempting to do electrical work that you are not qualified to do. Also, ensure that the active harmonic filter is properly maintained. Regular maintenance can help to ensure that the filter operates efficiently and reliably. The maintenance schedule should be based on the manufacturer's recommendations. Maintenance tasks may include inspecting the filter for damage, cleaning the filter, and testing the filter's performance. By following a regular maintenance schedule, you can help to extend the life of the active harmonic filter and prevent costly repairs. When troubleshooting electrical problems, always follow a systematic approach. Start by identifying the symptoms of the problem. Then, use the process of elimination to narrow down the possible causes. Use appropriate test equipment to measure voltages, currents, and resistances. Be careful when working with live circuits. If you are not comfortable troubleshooting electrical problems, hire a qualified electrician. Remember, safety should always be the top priority. Take your time, be careful, and follow all applicable codes and standards. In summary, the installation of the active harmonic filter requires careful attention to detail and a thorough understanding of the National Electrical Code. It's crucial to follow all applicable codes and standards to ensure that the installation is safe and compliant. If you have any questions or concerns, consult with a qualified electrical engineer or inspector.